Ding, and good morning.
Okay, thank you very much. Good morning, everyone. Before I start, I would like to explain few things. One is that I was asked by the chairman to give a talk about the Schrödinger equation, in fact, at the beginning, but then I thought that maybe I should not focus so much on Schrödinger equation, but say something more about laws of quantum dynamics. In fact, it should be quantum dynamics, not quantum mechanics. The title is quantum dynamics, right? But when I started to prepare all my slides, finally I found that I would like to say so many things about Schrödinger equation that, in fact, this is the part one of the talk, and I will focus mainly on Schrödinger equation during this talk. Okay, so but maybe in some future I will extend this also to some other quantum dynamics law. Before I start, also I would like to say something about assumptions which I do before this talk. So I assume that all listeners are aware about complex numbers, multivariable functions, differential and integral calculus, so they know how to differentiate and how to integrate functions, and also a notion of differential equations is also known for all the listeners. So these are basic. These are assumptions from the mathematical point of view, and assumptions from physical point of view is that you know something about Newton's mechanics, and you also understand basic notions of quantum mechanics. So the target audience for this talk is first-year PhD student. So please remember that I will not go very deeply with mathematical details, and also I will not extend much far away from the standard course on the quantum mechanics. So the talk is about quantum dynamics. If we want to say something about quantum dynamics, of course we should start from classical dynamics, because then it will be very easy for us to show the differences, all differences between classical and quantum dynamics, and also to find some similarities. So for this purpose, I will discuss only one-dimensional system and one particle system. Of course, this all things which I'm going to talk about can be extended, not always easily, to many-body dynamics, but we should start from something to make to give some framework in which we would like to discuss all these problems. So if we are talking about single particle in one dimension, then all dynamics of the particle is in fact governed by second law of dynamics, of classical dynamics, called Newton's second law. And as you remember from high school, this law says that acceleration, so the second derivative of the position of the particle, is at given moment is fully determined by the force, the total force, the force acting on the particle. And of course, this force must be divided by mass of the particle. So if we know forces acting on particle at given position, at position where the particle is at given moment, then we know the acceleration. And of course, this force is, if we have potential forces, we will assume here for simplicity that we have potential time-independent forces. So then the force can be calculated as a first derivative of the potential at given position. So this is the law of dynamics. And what is important in this law is that it is the second order second order differential equation. It means that if we want to solve it, we need not only the value of this of the position of the particle, but also the first derivative. It is clearly seen when we rewrite the second law of dynamics in the following form, that we rewrite the second derivative as the first derivative of the first derivative. And then this quantity we call momentum in classical mechanics. So then the second order differential equation we can convert to the set of two first order equations. The first equation is the equation which connects the first derivative with the second derivative. This is the equation of for the definition of the momentum, in fact. And the second equation is the equation which follows from the classical second Newton's law. So if we want to predict future, to determine future of the particle, we need to know the external potential. As you see, this external potential is present here, but because this set of equations, we have two equations, we need to define initial conditions for some chosen moment, t0. We need to give the value of the position and also the value of the momentum. So this is how the classical mechanics, the sense in which the classical mechanics is deterministic. The classical mechanics is deterministic, provided that we know external potential, which acts on the particle, or external forces in more general cases. And also we need the initial condition. Initial condition understood that we know all the positions and all the momenta at given moment. So then we can solve this classical equation of motions and predict future, and also to determine past, because if we know if we know these initial conditions and equations of motion, external potential, then we can predict not only future but also the past of the particle. So, and then we get the solution, the position and momentum for any moment. So how it works in practice, for example, the simplest example is harmonic oscillator, of course. So for harmonic oscillator, the potential is the following. This is mass times square of how it is called, frequency, right, and square of the position. So then equations of motion in this classical case have this form, and then we need to assume some initial conditions. So for example, we assume that at t equals 0 the position was some x0, which is known, and at the same moment initial momentum of the particle was equal p0, and then we can solve this problem exactly and determine future and the past, and one can easily check that this set of position and momentum fulfills this condition. So if we plug this to functions, to equations of motions, we will find that this is indeed true, that these two functions fulfill this equation of motion, and moreover, at t equals 0, x is equal x0 and p is equal p0. So the position and momentum at any moment in the future and in the past for this particle is precisely known. And this can be done for any classical system. In fact, if we know forces and we know initial condition, we can, of course, there are some pathological examples, as always in mathematics, for which these solutions are not unique, but typically, but these pathological situations in fact will not appear in nature, because in nature, nature simply does not like pathologies, and all situations we know from our observations are not pathological, and therefore the solutions are unique. So this is how it works in classical mechanics, and now we switch slightly to quantum mechanics. So in quantum mechanics, situation is completely different, because in classical mechanics, as you see, the state of the particle is at given moment is completely described by two numbers, right? Position and momentum. Position and momentum in the higher dimensions, these are not numbers but vectors, but still these are two quantities which determine the state of the system. In classical mechanics, situation is completely different, because the state of the particle is encoded in the wave function, not in one quantity or two quantities, but in the whole function. Wave, we call it wave function. And the wave function, I will say a little bit more in a few seconds about this, but the wave function is the object, a very abstract object, which encodes all the information which can be found about the particle with experiments. If you can imagine whatever experiment you can, and if you perform the experiment on a particle described by which state is described by the wave function, then you are sure that the result of this experiment is encoded in the wave function somehow. Of course, non-deterministically, because we know the interpretation of the wave function is not deterministic, but any information can be extracted from experiment about the state of the system of the particle is encoded in the wave function. This is the postulate of the axiom of the quantum mechanics. And this wave function is, in fact, a complex function over the configurational space. So what is the configurational space? For single particle in one dimension, this is a configurational space. This is the space of all possible positions of the particle. So configurational space, classical configurational space, is related for single particle is related to positions of the particle. So the wave function, quantum mechanical wave function, is a function, complex function, over all these positions. So instead, encoding the state of the system as a position and momentum, we encode it as a function over the all possible positions. This is the higher level of description of the particle. Instead of saying something about its position, which is uniquely defined for classical system, we change completely the language, and we say that the state of the particle is described by the function over all possible positions. So, and then this wave function, of course, has its own interpretation, which relates the wave function to experiments. So let us formulate this interpretation in the following. Let us assume that we have some configuration, classical configuration, which belongs to this configuration space. So if you think about a single particle in one dimension, this is some position of the particle from all possible allowed positions of the particle. Okay, and then you can, of course, for this given selected configuration, classical configuration, you can, and assuming that you know the wave function, you can calculate modulus square of this wave function at this, which is calculated exactly for this configuration. then this quantity, this modulus square of the wave function calculated for this given configuration is interpreted, and this is the postulate of quantum mechanics, is interpreted as a probability of finding the system at this given configuration, this selected configuration. So we have set of all possible configurations, all possible positions, and then we have wave function over these configurations, and modulus squared of the wave function calculated for a given configuration is nothing else but the probability of finding the system in this given configuration. Of course, if X, the configuration space, contains all possible, all allowed configurations, it means that all these if we sum up all these probabilities, they should sum up to 1, because the system has to be in some configuration and cannot be. And if we sum over all possible configurations, we should sum up to 1, because we are sure that the system is somewhere in this configuration space. So in fact, depending, of course, on the configuration space, we sum up or we integrate over whole configuration space. And if we sum up all these probabilities, we should sum up to 1. And this is quite natural consequence of this postulate that the modulus square of the wave function is the probability of finding the system in the configuration in given configuration. So as I tried to say during all this explanation, for single particle in one dimension, classical configuration space is simply all possible positions. So X belongs to the real numbers, right? We have all possible positions. And then the wave function is nothing else like a complex function of X, of all possible X's. And this normalization condition means that if we integrate modulus squared of X over all possible positions, we should give 1. So this is in this case, it works such a way. But look, if we know this psi of X, we can calculate many interesting features of the particle. So we know that the particle is in different positions with different probability which is determined by the modulus squared of X. But we can ask the question, for example, what is the mean value of the position? What is the mean position of the particle? Because particle is rather here, where the probability is high, and it's rather it is not rather in the places that where the probability is low. So we can calculate, for example, average position, right, of the particle. And this is quite easy because we know that this modulus squared of the wave function is nothing else like density distribution. And therefore, if we integrate this density distribution with X, we can calculate average position. We can calculate also any other quantities which are encoded in the wave function. Because as I told you, the wave function encodes all possible things, all possible quantities you can get from the measurement over the state of the system. And of course, there is also the assumption that if we repeat experiment many times with the same initial conditions, the state of the system will be always encoded with the same wave function. And therefore, this probabilistic interpretation can be experimentally checked by repetition of a given experiment, assuming that the wave function is exactly the same after in each repetition of the experiment, and then we can calculate this expectation values of different quantities. So this is how the interpretation of the wave function appears in quantum mechanics and wave function, concept of wave function. So the most important thing is that the wave function is a function over the configuration space, classical configuration space for classical system. This is the most important information. So instead of talking about classical configurations, we are talking about functions over configuration space, over the classical configurations. But here, please be careful, because there is some remark which I would like to put here, that quantum systems, we know, may have, and very often they do. So please remember that everything which I'm talking here about a single particle, for different systems, other systems may be much more complicated, because quantum systems may have internal degrees of freedom which completely do not exist in classical configuration space. And therefore, this notion of wave function is much more abstract, because it depends not only on classical configurations, but also may depend on degrees of freedom which have no classical counterparts. So in this sense, so the example is spin, for example. Spin has no classical meaning in classical configuration space, right? So if we have a particle with spin, which is internal degree of freedom of the particle, then the wave function depends not only on its position, but also depends on spin quantum number, which has no classical meaning. So there is no classical configuration for that. Okay, so please remember that there are some extensions in description of quantum systems which are completely beyond classical understanding. Of course, we can make some classical reasoning about spin and other internal degrees of freedom, but typically, if you try to make this interpretation too classical and you go deeply and deeply, then you get some contradictions on classical level, because on classical level, these notions cannot be well explained without contradictions. So please remember that in quantum mechanics, quantum systems may have these internal degrees of freedom which are completely not present in classical configurational space. But for our purposes and for our discussion today, we can assume that we do not touch these problems, and therefore wave function can be treated as a function over classical configuration space. So now let us switch to quantum dynamics, because up to now I was talking about interpretation of the wave function, but of course this is the wave function at given moment, right? We have the wave function of the system at given moment, and then of course we would like to have something like Newton's law, second Newton's law, to determine not only the present state of the system, but also to determine its future or in its past. And this is provided in quantum mechanics in the simplest case, by Schrödinger equation, which is the axiom of quantum mechanics. This is the postulate that the wave function evolve in time according to this differential equation. So now the wave function depends not only on the position or on the classical configurations, but also depends on time. And this equation determines how the wave function evolves in time. So we have two parts here. As you see, the first part is the differential operator of the second derivative on the position. So this is the one part of the right hand side of this equation, and there is classical potential here also sitting here. There is fundamental difference, however, between Schrödinger equation and the second Newton's law. As you see, the time derivative here is the first derivative, not the second. As you remember, in Newton's law, we have the second derivative, the acceleration. Here we have the first derivative. It means that you don't need to know anything else to determine the future of the wave function, to the evolution of the wave function. You don't need to know anything else but the wave function. You don't need to know its derivative, time derivative, and so on and so on. You just need to know the wave function. So the wave function completely determines its future. So if you give me the wave function and you give me the potential, external potential for the single particle, for this particle, then I can determine its future just solving this equation. If I know the wave function, I don't need to know anything else. So this is what I try to say here. If you want to determine the future of the wave function, you just to know the Schrödinger equation, of course, this external potential, and you also need to know the initial condition, so in fact the wave function at some selected moment. If you know these two things, so you know the wave function at some moment and you know the potential, you can determine future and also the past of the wave function. So from this point of view, quantum mechanics is completely deterministic theory. So on the level of Schrödinger equation, this is something which sometimes is missed in courses of quantum mechanics, I would say. That quantum mechanics is in fact deterministic theory. Deterministic in the sense that the wave function is completely, the time evolution of the wave function is completely well known and determined by the initial condition and external forces. Exactly as in classical mechanics it was, right? That the position at the momentum of the particle was completely determined by the external potential and initial conditions. Here, situation on the mathematical level is exactly the same. Quantum mechanics is deterministic in the sense that the wave function is completely determined in future. There is no problem with that. Of course, what is the difference? The difference is that the interpretation of the wave function itself is non-deterministic, as you remember. The wave function encodes only the probability of finding the particle at given position, not its position. And this is the difference. The difference is at the moment we try to interpret the wave function, or we want to connect the wave function with the experiment. As long as we do not talk about the measurement, the quantum dynamics is completely deterministic. And non-deterministic part appears because of the interpretation of the wave function as the probability of finding the particle and given position. So this is what I wanted to say here. So now, if we have this Schrödinger equation, we can ask many different questions. How different quantities evolve in time? Simply, exactly as in classical dynamics. So, for example, if we take the local density, so the local density, as you remember, this is the modulus squared of the wave function. So this is the product of the wave function and complex conjugate wave function, right? So we can ask the question, how this quantity evolves in time? So how the density distribution evolves in time. So how to do this? Simply, we just apply the first derivative to this density, and then we simply put this chain rule. We use this chain rule to calculate these derivatives. And as you see now, we can plug the Schrödinger equation here, and here we can plug the complex conjugation of the Schrödinger equation, and one gets the following. If you do it carefully, you will find that this potential part cancels completely, and you will get only this. And but this can be done further, because as you see, we have here the second derivatives. So the second one derivative can be taken in front of this whole animal here inside, and we end up with the following quantity. And what is interesting, this quantity is called probability current. Probability current at given position x. Why it is called probability current at position x? Look, if we integrate this density distribution from A to B, from some position A to some position B, then of course we get the probability of finding particle in the interval from A to B, right? So this is the integral. So if we calculate the derivative of this quantity, the right hand side is simply the probability current, whatever it means at the moment, is the probability current from A to minus probability current B. Okay. So this is this quantity, and now look. This is what I wanted to say, that this is the integral from A to B from the density distribution, and then we calculate time derivative. And this is nothing else like a change of the probability of finding the particle in the interval from A to B in time, right? So this is how fast the probability in this region decrease or increase, right? How fast it changes. And this is the difference between the currents at position A and position B. So nothing else like how much probability flows out from this region through A and B point, right? So this is why it is called probability current. So this is the evolution of this density probability, local density. And now let us think about other. If we have this evolution, we can calculate other things. So very interesting thing is the evolution of the average position. As you remember, average position is simply the integral of this density, local density times position. And if we want to calculate this time derivative of average position means, in classical notion, means average velocity of the particle, right? Because this derivative of the position over time derivative of the position is the velocity. So this is the average velocity. So we can calculate this. So this is simply, we plug in here this time derivative, and then we calculate. If you remember, this we calculated already on the previous slide, right? This time derivative. This was this probability current position derivative over the probability current. And here is something interesting, because we have function x times first derivative of x, first derivative of sum of the probability current over x. So this can be integrated out by parts. I hope you remember what does it mean, integration by parts. If you don't remember, just think about this equality, that if you have function times partial derivative over x, you can invert this derivative to the first function and keep the second function not differentiated, but then you need to subtract the product of the derivative of the product of the function. So if you plug it here, you will find that we have derivative of x over x, it's 1, and this derivative disappear, and this part also disappear because we integrate from minus infinity to infinity, and finally we get something like this. So the first derivative of average position, so the average velocity, is simply the integral of such an animal here, and then we can also this term integrate by parts, so we can shift this derivative over x from this function, complex conjugate function, to this function, and then we get exactly the same term as here, and then finally you get something like this. So you get the integral from the complex wave function times some operator, which is first derivative over x over the wave function. So simply, the average velocity is nothing else like expectation value. As you see, we have psi star here, we have some operator here and psi here. So this is the expectation value of this operator, this very strange operator, right? So this is the expectation. So this is the evolution of average velocity is simply proportional to this expectation value of this operator. We call this operator momentum operator because we know that average velocity, which is classical notion, average velocity is classical notion. Classical velocity, average velocity, should be proportional to average momentum, right? Because this is 1 over m times average momentum. This is because we would like to have the correspondence to classical mechanics. In this way we can introduce a momentum operator because this is quite natural way of thinking about average velocity as average momentum, as proportional to average momentum. So this is what we have. So in this way, we defined the average momentum, not only average position as previously, but thanks to the Schrödinger equation, we can also define average momentum. So now we can calculate time derivative of the average momentum, right? Exactly the same we did it before. So if we plug the definition of this average momentum to this time derivative, you will get something like this. We put the Schrödinger equation here, and in this case, the second derivative terms cancel each other, but the terms which are remaining are this potential. You can check that if you plug the Schrödinger equation here, you will see that we have something like this. So now we have the potential terms here. And this can be easily converted to the following form by integrating by parts of this part. Again, we get the expectation value of the first derivative of the external potential on position. So we get something like this. So nothing else. So the time evolution of average momentum is nothing else nothing else but the expectation value of first derivative of the external potential. So I don't know if you remember, but first derivative of the potential with this minus sign is simply the force. You remember the first slide of classical mechanics, so this is the force. So this is the expectation value of the force. This expectation value calculated, of course, in a given state of the system, which is encoded by the wave function. So we have something like this. Time derivative of average momentum, so this expectation value of the momentum, is equal to the average force acting on a particle described by the wave function psi at given moment. Okay? So let me write these equations once more. As you remember, average position is equal to the time evolution, first derivative of the average position, so the average velocity is proportional to average momentum, but time evolution, so first derivative of the momentum is proportional to the average force, right? So this is called Ehrenfest theorem. Ehrenfest theorem. So this is the theorem which says how expectation values of position and momenta evolve in quantum mechanical system for single particle in this case, when the evolution is governed by the Schrödinger equation. Okay, and just let me make a reminder here. As you remember, in classical mechanics we had something like this, that the velocity is momentum, right, and the time derivative of the momentum is the simply the derivative of the potential at given position. So as you see, there is a very huge similarity between these two equations. So the equation on averages is very similar to classical equations. But of course, in quantum mechanics, wave function encodes much more information than only average position and momentum, because we can also calculate higher moments of this position, higher moments of momenta, and these quantities are not encoded in classical equations. But the average is encoded in classical mechanics equations. As you see here, we have this expectation value, and this is important because you need to calculate expectation value over all positions, right? Because you need to integrate over all positions with the wave function, and this is why the dynamics of the wave function is not determined by the potential at given position only, but in the whole space at the same moment. So in classical mechanics, dynamics is dependent only on the local potential at the position where the particle is at given moment. Because in quantum mechanics, the position of the particle is not well defined, but only the probability of finding particle at different positions. You need to determine the time evolution of the wave function. You need to calculate expectation value or average force acting at different positions, acting on different positions, because particle with different probabilities is present at different positions. Okay, so now the final thing, how to solve Schrödinger equation, because now up to now I showed you some properties of Schrödinger equation, but finally we would like to solve the Schrödinger equation, right? So the Schrödinger equation can be written in this form, that we have time derivative of the wave function. Wave function depends on some configurations, classical configurations. This is the function over the classical configurations. And this time derivative is equal to some operator, which depends on this configurations and also on derivatives over this configurations acting on this wave function, right? So what is important, which I will not go into details here, but it can be proven that this, for any well-defined operator like this, standing in the Schrödinger equation, it is called Hamiltonian operator, Hamilton operator or Hamiltonian. For any well-defined Hamiltonian, well-defined meaning that defined for well-defined physical system, okay? One can find, and there is a prescription to do this, not always easy, but in principle one can find countable set of functions having the following property. So we have different functions for which, if we act with the Hamiltonian to this function, we get the number times the same function. These functions are called eigenfunctions of these operators, and these numbers are called eigenvalues of this operator. So what is important? You should remember that for any well-defined Hamiltonian, you can always find such a set, countable set. So countable means that you can count them by integer numbers, set of these functions. It is not easy, but in principle it can be done. Okay, so this is very important and very, very crucial thing here, because this with this theorem we can solve the Schrödinger equation. So assuming that we know, let me say something more about these functions. These functions are well normalized. It means that simply when you integrate over, so they have interpretation of wave function. So if you integrate them over all classical configurations, you will get 1. Sum up over all classical configurations. Sum up, of course, this modulus squared. Moreover, these functions can be chosen as orthogonal. So it means that you can find such a set of these eigenfunctions that if you calculate such a product of these two wave functions, so you have two different wave functions, these eigenfunctions, and you integrate their product over the whole configurational space, you will get 0 if these functions are different, and you will get 1 if this is the same wave function, because they are normalized. And moreover, this is the fundamental and crucial thing, that these functions form a basis, complete basis, in the set of wave functions defined over the same configurational space. So it means simply that if you have any wave function defined, well-defined wave function, so it must be normalizable and so on, but any wave function defined over configurational space, this wave function can be always decomposed uniquely to the set of these eigenfunctions with well-defined complex number here. So if you give me the wave function, I will give you the and you give me the Hamiltonian. In principle, I'm able to find eigenfunctions of this Hamiltonian, so functions fulfilling this equation, and I can decompose any wave function in this basis. So simply I will provide these numbers here. And this is fundamental and crucial thing, because this means that these wave functions form a vector space. You can think about these wave functions, these eigenfunctions, the space spanned by these eigenfunctions, you can think like a space, like a vector space. So you decompose any function into in this basis. Okay. So in fact, Hilbert space is a vector space, right? And these numbers can be calculated, provided that you know this function and you know this eigenfunctions. So with this knowledge, we are able to solve the Schrödinger equation. This is the final slide. How to do it? So to solve the Schrödinger equation, we of course need to know the wave function at some initial moment, t0, right? So let us call it psi 0. And how to do it? So first, we can think about the wave function at any moment. Wave function can be decomposed in this set of eigenfunctions of this Hamiltonian, right? Because we said a few seconds before that any wave function can be decomposed. So the wave function can be decomposed, and of course, in this case, these parameters depend on time, because at every moment, this decomposition is a little bit different, right? Can be different, but the only time dependence sits here, because these wave functions are not time dependent, because Hamiltonian is not time dependent. The same trick we can do with the initial wave function. Initial wave function can be also decomposed to this in this basis, and simply we get these numbers lambda k at given moment t0. Let us call, for simplicity, this lambda k of t0 as lambda k, and these are the initial conditions for initial decomposition of the wave function at moment t0. And then when we plug this decomposition to the Schrödinger equation we have here, we get something like this. And you see that on both sides we have time derivative of lambda k of t times function is equal lambda k times energy, right? Because Hamiltonian acting on phi is this eigenvalue. So simply it means that the Schrödinger equation we have here in red is completely equivalent to the set of equations for parameters lambda, this is the composition coefficients lambda, set of coefficients which and for each k, this Schrödinger equation gives you the following equation. And of course, for each k, you also have the initial conditions, condition lambda k. So you know this lambda k's, you know this energies, eigenvalues, and then Schrödinger equation is completely equivalent, so solving the Schrödinger equation is completely equivalent to solving this set of first order differential equations in time. As you see, there is no position here. These equations do not depend on the position, right? Because functions completely cancel out. And this equation, solving this equation is very simple because as you see, this is the time derivative of lambda is equal something times lambda. So it means that the lambda is simply the given by this formula, right? You can check that this lambda k completely fulfills this equation and also this initial conditions because lambda k at t equals 0 is exactly equal lambda k. So we have solution of lambda k. And it means that we have the solution of the initial Schrödinger equation because we can plug once more this lambda k of t here to this decomposition, and we get the wave function at any moment in future and in the past. So this is how we solve the Schrödinger equation. If you want, I can give you the example, harmonic oscillator. So for harmonic oscillator, for example, at t equals 0, the wave function, let us assume that the wave function is something like this. And then, so this is the modulus square of the wave function. And then after doing this procedure, which I described here, the evolution of the wave function, the evolution of the density distribution looks like this, okay? And we have the we completely determine the wave function in the future. If you change the wave function, initial wave function to something different, to the shifted Gaussian, for example, then the evolution is completely different. It's something like that, okay? So depending on the initial wave function, you get, for exactly the same potential, you get completely different evolution of the wave function. And here you have this blue line because you can remind yourself about classical equation of motions for the classical harmonic oscillator, which I showed you before. And this blue circle here shows the evolution of the classical evolution, solution of the classical evolution in the same potential. So as you see, this shifted Gaussian is something which can be interpreted as a quantum analog of classical particle moving in the harmonic oscillator. But this is, okay, I will not go further in details with that. Okay, so this is all I prepared for today. I think I'm over the time, so thank you for your attention.